Hello everyone. This presentation is entitled Dynamics Analysis for a Duopoly Game with Bounded Rationality on Cognitive Radio Network. So we began with the introduction, then we define the cognitive radio networks, the cognitive radio, then the system model and assumption, then we investigate equilibrium points and their local stability, then performance evaluation to validate our theoretical analysis. Finally, the conclusion to summarize. So a study by the Federal Communication Commission showed that the radio spectrum is partially utilized by the primary users or licensed users. So the idea of the cognitive radio is to share the spectrum between primary user licensed and so-called secondary users. Secondary users use the cognitive radio to detect this underutilized spectrum. The cognitive radio interface modifies its behavior according to the environment. In this project, we consider the computation between secondary users who use cognitive radio, who try to maximize the amount of frequency to be allocated according to the price of unit of frequency specified by the primary users. Means when the cognitive radio or secondary users are behave selfish, non-cooperative game. So what is the cognitive radio network? We began with the cognitive radio. Cognitive radio is a wireless communication system that uses methodology of constriction-based comprehension to learn from its environment and adapt automatically and instantly. The spectrum is divided into a number of block called channels. The radio waves are classified according to their frequency, and all these frequencies from the spectrum are divided into bands. So in this project we consider the spectrum allocation behavior. The behavior can be non-cooperative and or cooperative. In this project we concentrate in the non-cooperative, selfish behavior, when each user seeks to use spectrum in order to maximize his profit. The main function of the cognitive radio are detection and the decision on the allocation of valuable spectrum to the secondary users. That's an example of spectrum use on a primary user. This is a spectrum hole. So the secondary users detect this spectrum hole to share with the primary users. Move on to the system models. We consider a cognitive radio wireless network based on spectrum overlay having one primary users and two concurrent secondary users and one primary users. The primary users give at each secondary users the unit cost function of the spectrum of underutilized spectrum, the unit cost function, and Q1 Q2 transmit the requested spectrum allocation. This is the unit cost function defined as follows, where A and B are non-negative constants. So we modelize this behavior as a game, as a non-cooperative allocation game, where P are the secondary users 1 and 2, and Q1 Q2 are their strategy. Their strategy are the amount of spectrum shared by the primary users. and U1, U2 are the benefit or utility. The cost function for each secondary user, say E, is defined as follows, and this is the unit cost function multiplied by the requested amount of spectrum. The revenue of secondary user is defined as follows. Gamma 1 is the signal gain or channel quality of transmission, which is equals to the signal gain. The signal gain is equals to the average transmission rate multiplied by the revenue per unit. So the utility function of the secondary user is defined as follows: revenue minus cost function. So we model the behavior, the non-cooperative behavior, model the strategy of this secondary user, assuming that the requested spectrum of the concurrent secondary user is known and the requested in next step is equal to previous requested spectrum. Then the best response is defined as two-dimensional discrete dynamical system of the following form. But the problem is we don't know in real cognitive radio network, we don't know the requested spectrum of the concurrent. So we assume a banded rationality approach. Means that each secondary user, say 1, modify its requested spectrum according to the marginal profit. We will determine the expression of this marginal profit, and theta 1 is the adjustment speed parameter of the banded rationality approach. Theta 1 and theta 2 are the adjustment speed parameters of the banded rationality approach or learning rate. Theta 1 and theta 2. So the explicit of the profit function is defined as follow: the revenue requested spectrum multiplied by the signal gain or channel quality gamma, and Q1 is the requested spectrum multiplied by the unit cost function, which is given by the primary users. So the associated marginal profit is defined by this expression. We split this term, we obtain this expression. This expression is a function of the unit cost of spectrum, the requested spectrum, the unit cost of spectrum specified by the primary users. And this is the allocation, the spectrum allocation game. This is the marginal profit, and theta 1, theta 2 are the adjustment speed or learning rate. So we investigate the equilibrium point. At the equilibrium you have the requested spectrum at next time equals to the previous constant. Then from equation in numerical game we have this equation. Solving these two equations we obtain 4 equilibrium point. 0, 1, 2 are limit equilibrium, and this is the Nash equilibrium point, which is considered as the solution of this game. Means when the secondary users are satisfied their needs, this is the Nash equilibrium point, which is non-negative. So move on to the local stability of each point. Begin with the point. So to determine the stability condition, we use these criteria. When eigenvalue, when the model of eigenvalue of the Jacobian matrix is less strictly than 1, so this equilibrium is locally stable. So this is the Jacobian matrix for the maps associated to the game, the system game 7. Begin with this local stability of this point. This is a limit equilibrium point. According to stability condition, the point is very stable if the following conditions are true. This one and this one. This is the eigenvalue, and this is the another eigenvalue. Their model is less than 1. So this is the meaning of this condition. Move on to the stability of O1 and Q2. The associated Jacobian matrix at this point is defined as follows. We use the same condition, is less than 1, so we obtain this condition. And by the symmetry reason, we obtain the stability condition of the point O2. Move on to the Nash equilibrium, which is considered the solution of this behavior game. The corresponding Jacobian matrix is defined as follows. The characteristic equation to obtain the eigenvalue is defined by, since the discriminant is non-negative, then the two eigenvalues associated Nash equilibrium point are plus and minus. The stability condition, the same stability condition, is that the model of eigenvalue are less strictly than 1. We have this condition. G11 is the Jacobian matrix coefficient associated to the Nash equilibrium point. So if we give the value of channel quality or signal gain gamma 1 and gamma 2, we obtain a relation between the adjustment speed theta 1 and theta 2, for which the equilibrium, the Nash equilibrium point, is stable. Move on to the performance evaluation. We begin with dynamic behavior. So we set the initial strategy to, and the constant A and B, and the channel quality or signal gain to gamma 1 and gamma 2. For these parameters, the Nash equilibrium is found at 6 and 2. So we begin with the dynamic behavior of cognitive radio 1. For the value of learning rate, this is the Nash equilibrium at 6, and this is the behavior of cognitive radio under different value of learning rates, blue and red. We observe that for smaller value of theta 1 and theta 2, the behavior converges to the Nash equilibrium quickly, because when the value of the learning rate become larger, cognitive radio 1 take large step to converge to the Nash equilibrium. So the behavior may not be converged to Nash equilibrium, because it takes large steps and may not converge to Nash equilibrium. The same behavior with the conative radio 2. When the theta 1 and theta 2 are smaller, Nash equilibrium converge quickly. On the other hand, where theta 1 and theta 2 are larger, the behavior swings between two values and may not reach the equilibrium, may not reach the Nash equilibrium. Move on to the bifurcation diagram. For each value, we iterate the system, the dynamical system, to find an equilibrium point. So for value of theta 1 which is smaller, the Nash equilibrium is stable. But when the value becomes greater, bifurcation appears and finally chaotic behavior appears. The same for the conative radio 2. When theta 2 becomes larger, bifurcation appears and finally chaotic behavior appears. This is the bifurcation diagram under different channel quality or under different signal gain, when the channel quality becomes smaller, the bifurcation are delayed, and we have a larger stability of Nash equilibrium, and the chaotic behavior are also delayed. This is because when the channel quality become greater, when the channel quality are better, secondary users are willing to share a large quantity of spectrum. So the stability may not achieve it. Based on a relationship between theta 1 and theta 2 and given gamma 1 and gamma 2, we obtain the stability domain as follows for different gamma 1 and gamma 2, for different value of gamma 1 and gamma 2. The same when the theta 1 and theta 2 are smaller, the stability region is larger. But when the theta 2 and theta 1, the learning rate are become greater, the stability decrease, the stability region decrease. Also, for different value of channel quality, when the channel quality become larger, an example the green, the stability region becomes smaller. The intersection between this curve shows that when the channel quality becomes greater, the stability region becomes smaller. This is because of large steps. Secondary users take large steps to converge to Nash equilibrium, and so it may not converge to the Nash equilibrium. Move on to the global stability. One can see that when the initial condition are located at near to the Nash equilibrium, the basin of attraction become greater. So the Nash equilibrium is a fair and socially equitable solution for this competition spectrum allocation game. The increase in learning rates and the channel quality have the effect of instability on the adaptation of the spectrum allocation strategy. The users who use bounded rationality with suitable setting have a higher chance of reaching Nash equilibrium point. In future work, we hope to generalize this model to multiple player game as well as investigate other approach to model the competitive behavior of spectrum allocation. And thank you for your attention.